Welcome, everybody. A very unusual room, but already this one is packed, so I'm happy. Can you hear me? Oh, this is such a big room that I cannot shout out loud enough.
The online people definitely won't hear.
Yeah. So, welcome everyone. Yeah, pleased to see so many faces showing up to this really exciting talk today in our nuclear engineering seminar series. I hope you all had the chance to grab a snack and a drink. And I'm going to introduce now our speaker today, Dr. Scott Sepke from Lawrence Livermore National Lab. And he's going to present on the recent breakthroughs that the NIF, the National Ignition Facility, reported. So a brief introduction to Scott. For the past 16 years, Scott has been working at the Lawrence Livermore National Laboratory as computational physicist, working on multiphysics, radiation, hydrodynamics, with the code Hydra, supporting modeling of the inertial confinement fusion and other targets for the National Ignition Facility. His focus area is thermonuclear burn, neutron, light ion, and gamma ray Monte Carlo transport, radiochemistry, laser ray tracing, and laser plasma interactions, and generating simulated NIF diagnostics. So he is I would call world-leading expert on how to simulate inertial confinement fusion implosions. Prior to coming to Livermore, he completed a postdoc in physics and astronomy at the University of Nebraska-Lincoln, and he received a BSc, an MSc, and a PhD in nuclear engineering from the University of Michigan. So some Michigan alumni might walk up after this presentation and just chat about how Michigan is doing. And I heard there is a game as well tonight.
That's a Lions game.
It's a Lions game. Sorry, that's super. My bad. Anyways, without further ado, I give the stage to Scott, and I want to thank particularly Livermore in supporting his trip coming out. Scott jumped on a plane yesterday night to come out and visit to give you this presentation. Fully supported by Livermore, and he's going back home tomorrow. So this is literally just coming for you. And I think that is probably worth all a round of applause even before we get started.
All right. Well, what a wonderful introduction and welcome. So thank you very much. So so as you said, my name is Scott Sepke, and I'm from Lawrence Livermore, and I will be talking about this. And I'm representing Livermore here today. I'm the person who's talking about this, but this has been an enormous undertaking that has been going on for the last 50 years. So there's just been a huge number of people involved. More directly, I want to include the additional author list. A lot of these slides and a lot of my discussions on what sort of things to present at this presentation came from Annie Kreitzer, who was the lead designer of the Igniting Target, and Marty Marinac, who is my supervisor, my boss, and he is the head of ICF code and modeling at Livermore, and really the whole NIF team. So today I'm going to talk about, and I think probably most of the people in this room are aware that on the early hours of the morning on December 5th, 2022, we achieved fusion scientific break-even. So using inertial confinement fusion, we were able to put 2.05 megajoules of laser energy onto a target and produce 3.15 megajoules of fusion energy. And that was a first for any fusion device. There we go. Thank you. And again, I really want to emphasize how this is very much a big science project. This is a group photo that was taken at Livermore. You can see the building in the background is the National Ignition Facility. This was the group of people they managed to get to come out for this photo back kind of when people were still working remotely fairly regularly. So there are a lot of people not in this picture. So this is just a small sample. I'm not in this photo, for example. And these are just Livermore folks. In addition to Lawrence Livermore, we have collaborations involved in this project from Sandia, Los Alamos, University of Rochester's Laboratory for Laser Energetics, Diamond Materials, MIT, General Atomics, UC Berkeley, Princeton Plasma Physics Laboratory, many other universities, organizations, and CEA in France, the French Research Institute that focuses on fusion, and the Atomic Weapons Establishment of the United Kingdom, AWE. So this has been an enormous undertaking that's been going on, as I said, for many, many years. So as people know, I think nuclear engineers are keenly aware of energy needs, energy costs, greenhouse gases, and the need for green energy. Nuclear fission energy certainly has a role to play in all of that. And the question is, well, can fusion also be a part of that? You can see the statistic here that worldwide energy consumption is projected to increase 33% in less than 20 years. So we need good, clean, green energy and in large quantities. And so can the sun be our model reactor? So and I included this line here. This slide was actually made, and I included that the fusion is a potential clean, a limitless source of energy. And I don't know if anyone here is old enough to remember when nuclear fission was going to be said to be too cheap to meter. It was going to be limitless energy. And I saw somebody included that for fusion, and it made me chuckle a little bit. But it is true that there is a lot of hydrogen available in the universe. So I think we have a good fuel source if we can make this work, because it's the same source of energy that's powering the sun. So the sun's powered by fusion in its core, and now we've been able to replicate that in an energy positive way in the laboratory. And it's attractive for many reasons, and I think these are probably obvious to people here, or to many of the people here, that it is safe. The radiological footprint is very small. It is carbon free. Presumably, right now we've done the demonstration. We are nowhere near having a power plant, but this is a big milestone on the way to being able to produce fusion energy as an energy source for electricity, heat, other things that we need. And the idea being that this could then be part of the base load, just like nuclear fission reactors are, and not subject to vagaries like wind and solar can potentially be, where it's sometimes on, sometimes off, and this would just be power that could be on. Geological storage becomes much less of an issue. It's sustainable in that your primary fuel source is hydrogen. And also, coming from Lawrence Livermore National Laboratory, things like energy security and national security are always top of mind. So what is fusion? I want to start there. I think most people here will probably be aware, but let's make sure everybody has a primer of exactly what we're talking about here. So fusion occurs when two light nuclei are smashed together and actually linked together. So in this case, you can see this is the primary fusion reaction that is part of our experiments at the National Ignition Facility at NIF. So on the top left, you've got a deuteron. This is a heavy hydrogen, hydrogen 2. You have one proton, one neutron. In the lower left, you have a triton. So this is even heavier hydrogen, hydrogen 3. You have one proton and two neutrons. And if you push them together, overcome the Coulomb barrier, you have a probability that they will fuse together and create what you have in the upper right-hand corner. You have an alpha particle, so a helium-4 nucleus, and then a neutron, so they're in the lower right. And it turns out that you look at the masses, and the total mass of the reactants, the deuteron and the triton, is more than the mass of the products, the alpha particle and the neutron. And it's precisely this difference gives us the energy that is liberated. And fusion fuel is enormously powerful. So to get some kind of equivalency, you've got 1 pound of fusion fuel, so hydrogen fuel, is equivalent to 5,000 barrels of oil or 3.5 million pounds of coal, which if anybody has ever lived out on the Great Plains and seen the big trains full of coal, that's between 17 and 18 hopper cars full of coal in 1 pound of hydrogen could hold them. So there's a great source of energy here if we can harness it. And there are many approaches to doing this, and I've talked to people today who work on magnetic fusion, magnetic confined fusion. Today I'll be talking about inertial confinement fusion, and specifically I'll be talking about laser indirect drive fusion. And I'll talk about what that is as we move on. But there are other sources. There's direct drive inertial confinement fusion. There's magnetic drive. There's ion driven. And so there are all sorts of people that are working on various different methods for making fusion happen in the laboratory and making it net energy positive. They're advancing physics knowledge, they're advancing diagnostic capabilities, engineering capabilities, target fabrication, which is a very complex thing, and I'll show some examples of that shortly. And simulation capabilities have also advanced, and in lockstep with the advances in computing architectures and resources. Well, I alluded to this before. We've been waiting for this since 1972. John Nuckolls and some other people, including George Zimmerman, who is still active at Livermore, someone I work very closely with, proposed in 1972 Nature article that thermonuclear microfusion explosions could be driven with a laser. And this was an enormously exciting thing and really had an impact on Lawrence Livermore and their laser program. You can see on the bottom a whole series of lasers that were built in support of this, beginning with the Cyclops, and then moving up to Janus, that was just 10 joules, and then Shiva and Argus and Nova, which was up to 40 kilojoules. And the original estimate was that you could get fusion ignition with a laser that was about 100 kilojoules or less. And then they started doing experiments on Nova and realized probably going to need something bigger. And so that is what led to the National Ignition Facility being built at Livermore. And here you can sort of get a scale of what the National Ignition Facility looks like. It's a collection of 192 laser beams. You can see the long, I don't have a pointer, unfortunately, but you can see the long racks there, sort of in the center left are the long amplifiers. And that part of the building is equivalent in size to 3 football fields. This is a very large building. And all of those lasers go into those red pipes on the right-hand side. The way the optics, all the laser beams are piped through there. There are 192 lasers. And they are all piped into the target chamber, which you can maybe see is there's a sphere over there with where all the beam pipes are converging. And then there's a cutaway of that in the upper right. So that the scale of that chamber is 10 meters. Inside of that are gold hole realm, which I'll describe more, but the gold can or hole realm that our target sits in is then shown below that. That's a scale of 1 centimeter tall. And inside of that is the actual fusion target, the capsule. That's 2 millimeters in scale at the beginning. And it is imploded to a burning plasma that is about half the size of a human hair, a few tens of microns in diameter. So what is inertial confinement? Laser indirect drive inertial confinement fusion. This uses a laser to drive a hole realm that creates X-rays and drive the implosion. So you can sort of see the sequence of events here. Starting on the left, you can see 96 laser beams going to the top of this gold can we call a hole realm. 96 beams are coming in through the bottom, and they're all aimed at the inside surface of that hole realm. From there, as that ionizes, it heats up and ionizes, it will begin to generate an X-ray bath, whose temperature will get up to about 300 electron volts. Those X-rays then interact with the capsule and begin to heat and boil off and ablate the outer surface of the capsule. Everybody here knows about Newton's laws that for every action, there's an equal and opposite reaction. So as that material is ablating off, as it's boiling off, that will create a drive force to drive shocks that will implode the main core of the capsule, the fuel of the capsule. Eventually, the fuel core will reach pressures of 500 billion atmospheres, and thermonuclear burn will initiate. And when everything comes together right, as it did last December, your burn will produce more energy than the lasers brought into the target. Now, achieving these conditions, though, demand very, very precise control of the design of the capsule, the design of the hole realm, the laser itself as it's firing, the pulse that you request, and then what actually is being able to be delivered, and the uniformity of the pulse that's being delivered, as well as the target that's actually manufactured. And these targets, the lasers, the diagnostics we use, the computers, the codes, everything we use, they're truly engineering marvels. You can see here in the upper left, there's one of our hole realms and its holder arms. And the LEH is marked at the top. That's the laser entrance hole. So you have to get all 96 beams through that top hole and then a similar hole on the bottom. As I said, it's about 1 centimeter tall. Inside of that is suspended at the very center, at a very tight tolerance, the target, the capsule target. And it is suspended there by a very thin membrane that's it's a few tens of nanometers thick. We call it the tens. And that holds the capsule in place. And on the right-hand side, there's an X-ray radiograph of one of these capsules. Now, in reality, it's about 2 millimeters in diameter. You can see it's blown up here, and there's the very outermost light gray region is just looking down through the hole realm, so you're just seeing down through the bottom. But then you get to the outermost gray layer, and that is it's high-density carbon. Our target's made out of carbon, or it's in a diamond crystalline phase. And then on the inner surface of that diamond, there is a few atom percent dopant of tungsten that's used to keep X-rays and electrons, primarily X-rays, from preheating the fuel. And inside of that, there's a little bit of a round haze in there. There's a lighter surface. That is the deuterium tritium fuel, and it's been frozen out. So you now have a hydrogen ice layer on the inside, and the inside of that is deuterium tritium vapor. And this is all, it has to be, to freeze this hydrogen, it has to be cryogenic. So this is at about, I think, 14 to 18 Kelvin. So this is very, very challenging to field and to grow this layer. The layer is grown once the target has been positioned at the center of the chamber. And the deuterium and tritium are not added until the very last moment, well, when the experiment begins. Oops. You can see in the lower left-hand or lower right-hand corner, there's a little fill tube, and there's just a tiny glass tube that the fuel is actually brought through. And originally these were, well, I think the very first ones were IVF tubes. And they were the ones that were used at the beginning of the National Ignition Facility experiments were about 20 microns in diameter. And it turned out that was far too large. It was making far too large a perturbation and causing material to be launched into the capsule. So the target fabrication people performed a minor miracle, and now they're able to field these at either 5 microns or even 2 microns in diameter, which is just impressive to me. So to achieve fusion ignition gain in our ICF experiments, we have to heat and compress the DT fuel. And these are some very extreme conditions. And you have to be able to hold it there long enough for there to be appreciable burn. As you can see, the sort of a schematic equation in the upper left, the D plus T gives you a neutron and an alpha particle. And that alpha particle plays an extremely important role, because once you've compressed the plasma, that alpha particle is then going to slow down and stop. So it's going to have a whole series of very small Coulomb interactions, Coulomb scatters, deposit all of its energy into the center of the burning plasma. And hopefully then that energy will continue to heat the plasma faster than that plasma is losing energy by conduction and radiation. So you've got this hot spot that's burning in the center, you've got cold, dense, or colder, dense fuel around it, and then you still have some diamond ablator around that. Now, if everything just comes in perfectly 1D, it's all going to smash down, and everything is perfect, it will burn, and it will ignite, and it will run away with itself. But unfortunately, this is the real world, so the capsules have scrapes, they have divots, they have material, junk inclusions in them, and you have just instabilities. You're pushing a light fluid against the heavy fluid. You're going to have Rickmeyer-Meshtoff instabilities, Rayleigh-Taylor instabilities. They're going to give you this sort of, you can see all these little bubbles and spikes, this really mottled, messy surface. And if things get too rough, you're now going to start poking that high Z material, the carbon, into the burning plasma. Well, now you're adding extra electrons that can provide extra radiation. You're going to have energy loss via radiation. You're also increasing the surface area of your hotspot, which means you have more opportunity for conduction to lose energy. And so it's all a race. You need enough alpha particles to deposit enough energy inside the burning part of the fuel fast enough that you will overcome all of those losses and actually be able to begin to burn what is initially the colder, denser fuel. And there are a lot of design considerations to make this happen. It's one thing to say, well, okay, we can kind of conceptually do this, but we're very limited in the laser power, laser energy, what the target fabrication people can actually build. So you have sort of a limited space that you can work in. And so what are the things that the designers have to think about? Well, they have to think about the adiabat, the amount of entropy that is created inside of the center of the capsule. If you make it low entropy, you can compress it farther. Easier to, you then have more kinetic energy from the shell coming in to convert to thermal energy. That's good, but that will also can lead to instability growth, the hydrodynamic instability and other problems. And, as you're coming in, everything is growing as R cubed, as everything is imploding because it's a spherical implosion. So hydrodynamic instability becomes an issue. And like I said, you can have the conduction losses, the radiation losses. You also want to make sure you try to maximize the kinetic energy of your shell as it's coming in, so you have the maximum amount of energy to convert to thermal energy, but you need to also consider the low mode asymmetries. It's almost all but impossible to drive these things in perfectly round, but any out of round is now going to make your stagnation less efficient. You're going to be less efficient at converting all that kinetic energy to thermal energy and doing it all simultaneously. And of course, Murphy's law always takes over. What's best for the implosion is usually very difficult for the hohlraum to produce. So remember, we had that gold can, and hohlraum, it can produce X-rays that make the drive for the capsule, but you have to work within the constraints of what you can generate inside of that. And so this is where the design phase comes into play, and the use of our models and design codes. These are both results from Hydra code, the Hydra multi-physics radiation code, which I am a developer on, one of a team of several people. And so we do two sorts of simulations. We do beginning to end all the way through calculations, as you see on the left here, where you model everything from the beginning. So the laser entering into the hologram response, the capsule response, and this is based on some of the experimental data that comes before us. So the shock propagation and the initial stage of the shell implosion, you can see some of the data there, will inform when we actually do an ignition shot. We can do these at moderate resolution. So if you're familiar with spherical harmonic decompositions, we can get up to about mode 10, mode 30, something like that. So we can capture some of the lowish mode, low to mid mode features, but we can't get everything, all of the noise and all of those little fingers and bubbles and spikes that we saw in some of those schematics earlier. So another tack that we take is we are able to extract the X-ray drive that impinges on the capsule from those hologram calculations and transfer it into a calculation where we just model the capsule implosion. And those we can model at much higher resolution in both 2 and 3 dimensions, up to easily mode 100, 200, and up to a few to several thousand for dedicated calculations. And so the compression I've alluded to, the X-ray drive is launching shock suit plasma and driving it. So how does all this look? Well, you can see on the left-hand side, the lower the gray traces are 2 different laser pulses. So it's a stage step-shaped pulse that is designed to produce 3 separate shocks to traverse the capsule and coalesce and merge right near the inner surface of the ice. Remember, when we saw that image, we saw the ablator, the tungsten doped layer, and then the ice. And so there are various design considerations that come into this. So how long do you want the laser pulse, within the amount of energy you have? What power do you set it to? And what is the temperature? What's the X-ray response to that? And so you're accelerating the fuel to very extreme velocities. The fuel at its peak velocity is going about 400 kilometers a second. So you've got a fair amount of mass all coming in very fast. And you want to then very quickly stagnate that fuel and create the thermal energy that's going to give you burn. But you also have a light, as I mentioned before, you have a light fluid that's pushing on a heavy fluid. You're going to have instability problems. As you can see, there was a calculation here done by Dan Clark, one of our design physicists. And you can see it's 2 plots smashed together. So on the left, you've got the DT fuel, sort of on the bottom, and on top, you've got the high density carbon, the HDC, the diamond ablator. And you can see that their instability has built up here to some degree. And you can kind of see there's modeling in the color scale. And on the right, you have the mass density. And there it's a little clearer to see where, there's a lot of messiness going on here. It's not a nice 1D calculation. And this is at 1/6 of the original radius. We're going to implode this thing all the way to 1/25 of its original radius. So these instabilities are a very important issue. But ultimately, once you make it all the way in, your core pressures should be about 500 gigabars, densities are about 50 to 100 grams per cubic centimeter, temperatures greater than 10 kilovolts. So these are pretty extreme plasma conditions. And then that's surrounded by the compressed shell, and you can see the sort of typical parameters there. So I'm going to shift to a little bit of a history lesson. So how did we get here? How did we get to ignition? And we have come a long way since experiments started at the National Ignition Facility in 2010. And the figure of merit that I'll be quoting through all of this, the name that was given to it was ITFX, and that name isn't important. But the figure of merit is the amount of energy, internal energy in the hotspot times the pressure of the hotspot squared. And you want that to be hot. And so on this plot on the right, then we're going to kind of step through the history of experiments at NIF on this plot. So the hotspot energy is on the x-axis, the pressure is on the y-axis, and you want to be in the upper right. You want both of those things to be maximized. And sort of above and to the right of those curves is where ignition happens. And so in 2010, experiments began, and we started with what we called the low foot. This was a very low entropy design. And what you see there are 3 sort of 3D renderings. You're looking at the density and the temperature of big 3D calculations of these capsules. And you can see the low foot on the left, the yields that we got out of that were about 2 kilojoules from almost 2 megajoules of laser energy in. Not exactly a success. And you can see there are a lot of really ugly features on that. The big spike sticking out of the right was that fill tube. They were still about 20 microns then, and that was causing a huge perturbation. You can also see there's sort of a ring around the top, almost like a hat on the top and on the bottom. And that was where that cellophane, that few nanometer thick cellophane that holds the capsule in place, where it lifted off the capsule. And that caused terrible problems for material stability. And you can see it was just tearing up the capsule. And we saw this in these high resolution simulations. And before that, we actually saw it in the data. It was really a horrible, we call it the tense scar. And really very dramatically impacted the compression. This is back when our capsules were made out of plastic. So from there, the National Ignition Campaign ended in 2012, and we'd gotten a few kilojoules out, and everybody was very disappointed. So then we moved on to a new design that had higher entropy, less compressible, but less susceptible to hydrodynamic instabilities. And you can see the instabilities are a lot less. It's a rounder capsule, but you can still see that fill tube feature on the right. You can still see the tense scar. This is not an ideal design. And at that point, we decided to change ablators, and we moved to HTC, the high density carbon diamond ablators. And now we did experiments that followed on from that, and we got the yields up to 55 kilojoules. So again, a not insubstantial improvement. If you look at the figure on the right, you can see, okay, the low foot, the 2 kilojoules was down in the lower left. The high foot was 27 kilojoules, and the pressure moved up. And again, the HTCs, the pressure moved up again. But you notice the hotspot energy isn't increasing. So we're not really moving very quickly toward that curve in the upper right where we need to get. And we were out of laser energy and laser power. We could not push this any farther. So a rethink had to happen. And so the idea was we moved on to what was called the hybrid campaign. And it was to try to take everything we had learned and take the best pieces of everything. Think about those 4 factors I mentioned before: the entropy, the hydrodynamic instability, the velocity and late time ablation pressure, and the low load asymmetries, and think, how can we improve? And so the idea became, let's make the HOROMs more efficient, make the capsules larger, and see if we can keep the pressure high and get the internal energy in. And so that is what happened. The problem here was, and now we're looking at a couple of close-ups of sort of mock-ups and simulations of the HOROMs. The lasers are coming in, and you've got some that are illuminating, say, the very top of the HOROM, and some that are illuminating the middle of the HOROM, so right around the equator of the capsule. But the capsule being so much larger, you've got a bladed diamond, you've got a bladed gold. The lasers that are trying to get to right around the equator of the capsule are getting absorbed before they get there at late time. And so you can't keep the capsule round. And so we'd played around with something and haven't used it a whole lot. It's something called crossbeam energy transfer. And we actually take advantage of a plasma instability where you are able to use, if we detune the wavelengths of the lasers just slightly, a few angstroms, you can use the ion acoustic wave that gets generated by the lasers overlapping to actually transfer energy from the beams that are illuminating the top of the HOROM to those illuminating around the equator. And so you don't have any more power from the laser, but you can get power from those outer beams and move it to the inner beams and help bring the capsule back into round, which was, I think, a real success of plasma theory in this whole process, was predicting this could happen and then actually making it happen in the lab, and to our benefit. So the first experiments happen with these new hybrid design, and you can see there's a cloud of particles sort of around the 4 to 8 kilojoule hotspot energies, but the hotspot pressures went down. They were 200 gigabar and lower. But just shrinking the size of the capsule, just 50 microns, was enough to bring that back. So now we've gotten back to the high pressures we had before, where we've significantly increased the hotspot energy. And look, we've gotten much closer to that curve, the ignition curve that you see with those dashed lines. But we weren't quite there. But there were some clever people. The designers spent a lot of time trying to play with things and look at it all, and look at all the options. And they realized that if they lower the laser power a bit and extend the pulse a little bit, so they keep pushing on it until right at the moment that the capsule is imploded all the way, we're able to take the next big step, which was on August 8th, 2021. That was the day we had our first big party at NIF. We got over a megajoule of energy out. So it was 1.8 megajoules of energy, and we only got 1.35 out, but we exceeded the Lawson criterion. And that was a big deal. That had also never been done. And we were over a megajoule of energy. This is a huge number of neutrons. There's a lot of great physics we can do. Neutron physics, and the people here in this room, I'm sure, can imagine ways you could use that. And so I love this slide because it sort of captures the sort of the feeling and the mood at the lab for many years. And it's a bar graph of the fusion yield over years. And you can see for the first several years, you can't even see the bars, and then kind of slowly goes up, but everything was very low. And then starting in around 2020, COVID hit, and we actually started really making very serious progress with this hybrid campaign. And we were able to beat the megajoule, and lots of excitement, lots of optimism. And then we tried to repeat the 1 megajoule, and we were not able to get capsules that was clean. The 1 megajoule shot, or 1.35 megajoule shot in August of 2021 was particularly clean and smooth and just sort of an ideal capsule. And the follow-ons were not. They were just not quite as good a quality. They were still good capsules, but not that stellar quality that one was. And it turns out that made a huge difference. We were not able to get over a megajoule again. But somewhat coincidentally, the lab had been working to upgrade the laser. And so we had been maxed out at 1.8 megajoules. And the laser folks around this time came to us and said, well, we've done some upgrades, and now we can give you 2.05 megajoules. What can you do with that? And we said, well, okay, we've got more energy. So now we can push on these capsules harder. So we can make them slightly thicker, and they'll be more robust to the instabilities we were seeing before. So, okay, we've got these capsules that aren't as clean and aren't as smooth, but now we have more energy to be able to push on. And between that and some improved design considerations, we were able to improve, and we had our first, skip this. Yeah, I guess I've already said all of this, and I'm just going to skip ahead to the punchline. So then our first attempt with this higher energy pulse with the slightly thicker capsules was on September 19th, 2022. Everybody was excited. We thought, oh, this might be the one. This might go. Predictions were that there was a decent possibility that we could get this one to ignite. And it did give us over a megajoule, but it still did not ignite. It did not give us more energy than we put in. So we still had not hit break even. But it was a good proof of concept that it had 20 times more high atomic number inclusions, or just kind of stuff polluting the ablator, but it still gave us over a megajoule. And so that gave us cause for optimism. And it was also noticed, you can see in the lower right, these are X-ray images on the left, you have the 210808, that's August 8th, 2021. That came in round and gave us the 1.35 megajoules. But then the September 19th, 2022 shot on the right, it's what we call pancaked. It's sort of smashed. It's not round, but it's sort of flat. I said, okay, if we make this round, simulations predict that it should ignite. So we had to fix the shape. And this was when we came back to, well, we have this crossbeam energy transfer. We can take advantage of laser plasma instabilities and transfer more energy from those outer beams at the top and the bottom of the horon toward the center. And this was to try to give us a better energy balance. And in fact, it worked. And so you can see here on the right-hand side, this is a reconstruction. We have neutron imagers on multiple lines of sites. So Los Alamos was able to reconstruct what the 3D neutron source looked like, and it came in very round, and it gave us 3.15 megajoules from 2.05 incident. And there it was. We did it. And there was a party at Livermore. Everybody was very, very excited. And then we had to keep it quiet for a little while before the official announcement, and it all came out, and I'm sure many people here heard about it. And it was in the New York Times, which made us all very excited. You don't get recognized that way very often. So it's been exciting in that way. And many of us have gotten to come out to places like this to talk about this and hear people be excited about it. And it's just been a very wonderful thing. And it's a great proof of concept. But of course, then the next day you go back to work and you say, okay, well, what do we do now? And so there's still a lot to do. And there's now increased interest in inertial fusion energy approaches. And there are a lot of different techniques, a lot of different companies working on it. There are also a lot of people working on the magnetic counterparts. There's been a lot of work on that for many, many years, as people here are very aware. But our goals are now working on higher gain designs, working on improving the engineering, working on just all of the things that need to happen for inertial fusion energy, IFE, and figuring out how to make cheaper targets, more efficient lasers, all the different pieces that would have to come together to get from where we are now to actually thinking about putting energy on the grid. And there's a very long way to go, but there's a lot of interest, there's a lot of optimism. There are a lot of new players getting involved. And so it's a really exciting time to be doing this. And I would be remiss if I didn't spend a couple of minutes to talk a lot about just, well, what are the details of the experiments, but we would not be able to do these experiments and do our design work and have gotten to this point without things like, for example, the diagnostics. These are some of the best diagnosed plasmas, certainly some of the best diagnosed fusion plasmas in the world. We're able to measure the DT ion temperature, the burning plasma ion temperature, the bulk hotspot velocity, and the neutron yield, all from our time of flight to magnetic recoil spectrometer. The time of flight detectors are a magnetic recoil spectrometer. We're able to map the DT, the dense DT fuel uniformity and density, the aerial density of that fuel using nuclear activation diagnostics, as well as Compton radiography. We're able to measure the DT neutron yield from zirconium activation foils. We're able to measure the hotspot size and shape and the fuel shape from neutron imaging. We're able to, in some of the experiments, we also look at the ablator shape by doing gamma imaging of the carbon. So there's a neutron inelastic scattering from carbon that gives us a gamma image. We measure the hotspot amount of mix using X-ray images and X-ray spectroscopy, and we're able to measure nuclear burn widths and the peak nuclear production time using our gas Cherenkov gamma ray history diagnostics. And these are diagnostics that have been produced and maintained by people from several different facilities, Los Alamos and Livermore and MIT. And it's really been a wonderful collaborative experience making all that happen. And it's a real joy to be able to diagnose these plasmas. So when we run our codes, we can actually produce synthetic diagnostics to say, hey, okay, how good a job is our code doing on matching the data? Where are we falling short? Where are we getting things right? And what do we need to change to actually improve what the diagnostics are showing us? And modeling these implosions is also a very challenging computational task. I mean, the design work was all done with 2 and 3D simulations. I described a little bit about before. Though the pre-shot business, so the design is done, we say, okay, this is the target we want to build based on those calculations. The experiments happen, the data comes in, and then there's a post-shot stage where people say, okay, now let's go back and do a post-mortem. Let's model it using the actual as delivered laser, the as shot target, and all of those details. And to do that, we do that in 2 dimensions, we do it in 3 dimensions. And in doing that, you have to account for many different physics effects. You have radiation transport, you have conductivity, you have shock hydrodynamics and the instabilities, and you have to resolve those. You have thermonuclear burn, you have particle transport. These are inherently 3D objects. We get away with doing a lot of 2D calculations, but we would have been nowhere near where we are now if we had not been able to do these kind of 3D, even some of these very large, like you see here, one of these 3D hero calculations, where the laser drive imperfections, the target imperfections, real target features, grooves and inclusions and divots are included. And we have to be able to model this over huge spatial scales. You've got nanometer scale defects, micron scale features, millimeter scale capsules inside the centimeter scale horons. And it's daunting sometimes to think about all that happens, but we are able to do it. At scale, these hero calculations, like you see on the right here, these 3D calculations have been done upwards of 200 million CPU hours, including up to 2.6 billion zones on 200,000 CPUs. So some of these are very large. A more typical design calculation uses about 64 to 128 cores and takes about a day or around a day to run. And we are fortunate at Livermore to have access to some of the greatest computers in the DOE complex and really in the world. So these are sort of three classes of computer, three of the different sets of machines that we use. We have Jade and Jadita and Mica and Magma are day-to-day workhorse machines, and they've got 181,000 cores, 8.9 petaflops. These are our day-to-day operating machines. We use the Los Alamos sited machine Trinity. It was almost 1 million cores with 41.5 petaflops, and it was number 6 on. It was the 6th largest computer when it was introduced in 2015. And our newest large-scale capability machine is called Sierra, with 1.5 million cores, 125 petaflops, and it was the second largest computer when it was introduced in 2018. And coming online in the next several months is El Capitan, which will be even larger and sited at Livermore. So we are very fortunate to have these kinds of computing capabilities to attack these things. Let me focus on the last. I've got a few minutes left, I guess. I'll focus a little bit more on my little piece of this pie. There are so many people involved, but my little piece of the pie is in modeling, and more specifically on the code development side of the modeling. And so I work on the code Hydra, which is a 2D, 3D multi-physics code. Block structured mesh runs on 2D quads or on 3D hexahedrons. And I've already mentioned why 3D simulations are important. And it began life back in 1994 with a guy named Bob Tipton, who's been a long time code developer at Livermore. And he began writing a 3D hydrodynamics package. It was about 50,000 lines of code. And Marty Marinac, who I mentioned is my boss and the head of ICF modeling now, he took that and ran and started just bolting on the pieces, all these other pieces of physics that were needed, and turning it into a larger and larger code, and spending lots of time testing it against experimental data, against other codes that have been validated, and really working hard to make this a verified, validated code. And over time, now the team has grown. We've gotten slightly larger. So now it's Marty and Gary Kerbel, who's now retired, but still works with us some, and Mehul Patel, and Joe Koning, and Chris Schroeder, and I. And then Britton Chang is also retired. And we have Milan Holef is working with us now for a while, working on discrete ordnance solution for radiation transport. And this is a moment where it's really, the code has really benefited from our collaborations at Livermore and other sites. And it's really been a group effort, and these big science kind of efforts. But now, today, Hydra includes a broad range of physics packages, electron and ion conduction and electron ion coupling. I'll show the whole list, or mostly a list on the next slide, but it's now expanded to approximately 1.3 million lines of code, and is used for design and simulations of a lot of ICF targets. So the laser indirect drive that I've talked about today, laser direct drive, which many of you might be familiar with, where instead of using the lasers to heat the hohlraum and create X-rays, just drive the capsule directly with lasers. Magnetic drive fusion, for example, the experiments that happened with Z machine in New Mexico, heavy ion driven fusion, and other high energy density targets from modeling is done at Los Alamos, Sandia, Livermore, the Laboratory for Laser Energetics, and several universities. Well, Hydra is the primary 3D design tool at Livermore. You can see this, I like this bubble plot. It kind of gives you an idea of the breadth of physics packages that have to be included. It is massively parallel. It's parallelized with message passing interface, the MPI. It's also thread parallel with OpenMP and POSIX threads. And we're beginning to get some of our packages running on the graphics processor units. The Sierra machine and the El Capitan I mentioned have a significant number of their floating point operations on graphics processors. So we're ticking off things one by one. The more computationally expensive things we're getting onto the graphics processors, as it makes sense. So Gary Kerbel, that retiree I mentioned, is getting our INC photonics up there. My little corner of the world here, Florian gave a list of the things that I work on, but is the bubble in the upper right and the bubble in the upper left. So Monte Carlo transport, well, thermonuclear burn and the Monte Carlo transport of the burn products, and 3D laser ray tracing and the laser plasma instabilities that are associated with that. And I will just kind of go through briefly what those models look like. I'm not going to get into a huge amount of depth here, but maybe they'll spur some questions. So our Monte Carlo burn capability computes the mass, energy, and momentum deposition, as well as all of the nuclear diagnostics. So we have all of these are the standard fusion reactions we include, but users can include any they like. See in the box there. And all of those products are transported by Monte Carlo And then the energy, momentum, and mass deposition is then fed back into Hydra. So it's a self-consistent transport. And then we also are able to tally an enormous array of things. So we're able to model all of the nuclear diagnostics I mentioned from the output of this Monte Carlo. And it has been extensively tested against simple test problems, experimental data, as well as just being able to model the NIF data and diagnostics that we observe experiments. So it transports neutrons, the hydrogen isotopes, the helium isotopes, so that will include things like the protons, deuterons, tritons, the alpha particles. It also will transport gammas in 1, 2, and 3D. It's MPI and thread parallel. I mentioned the tally capabilities. It uses the Livermore nuclear data set, which we have good confidence in for the light isotopes that are relevant to ICF. And we use this both for the integrated, the capsule and Horon calculations, as well as those high resolution capsule only calculations I mentioned before. And all of the transport is relativistic. And it turns out that this is actually relevant. 14 MeV neutrons, as well as the 14.7 MeV D plus helium-3 fusion protons. They have a relativistic factor of 1.015-ish, which isn't very high, and you might think you can just ignore, but it actually turns out that we have neutron time of flight detectors at NIF that are 20 meters from the target, and the arrival time would differ by 272 picoseconds, which is actually measurable. So we include the relativistic effects in all of the transport. Charged particles primarily are modeled using a simple continuous slowing down model. We include slowing down from free electrons, bound electrons, and ions. The free electrons are the primary slowing down mechanism. And so that's where the most detail is. We use a Born random phase approximation method that includes effects of Fermi degeneracy, which is needed. What I quote here was a fit from the data from a paper by Maynard and Deutsch that has been a standard at Livermore. But a few years ago, we did some studies and realized that the Fermi degeneracy corrections needed a little bit of tweaking. So we've actually improved upon that a bit. For the bound electrons, we use a standard beta block model out of any of your textbooks like Knowles, nuclear measurements. And we have a very simple model for the ionization potential. It is important at the very early stages to use the bound electrons. And then the ions just use a simple heuristic binary collision model. We also include the effect of large angle Coulomb scatters. So say an DT alpha particle screaming across the hotspot will have large angle scatters with some of the background deuterons and tritons, and we can self-consistently bring those into the transport calculation and transport those, which gives us in-flight reactions, which we have measured in dedicated experiments and on NIF experiments, standard NIF experiments. And we also the way we account for the deflection due to small angles is we have a model it's a little bit crude, but it will maintain the RMS deflection. And so our particles move in straight lines and then have their trajectory updated at the end to account for that. We also, in a similar way, can include the effect of magnetic fields, even for the relativistic transport, which was a cute problem to have to work out. And I see it as 450, so I think maybe I will skip my laser ray trace and just go to the end. I'd say that this is a very exciting time to be doing nuclear engineering, to be doing nuclear fusion and plasma physics research. There's no end of things that still need to be answered. This milestone is a big celebration for us, but it's really just okay, now there are big problems to solve. And lots more to do. But there's a lot of optimism and energy and interest. And it's what's brought me here today. It's what makes me excited to get out of bed, and has been a lot of fun to talk to a lot of people already today about all of this. Thank you for your attention.
So thank you very much. I'm going to be the MC for the Q&A. And I'm trying to go to, we're going to check the online questions. Do we have any other graduates here that have questions to ask? Graduate work as well. So go ahead, please.
With this type of code, with like you mentioned, it's very multi-physical, very multi-scale, both on time scale and space. How can you elaborate a little bit more exactly how do you, with your techniques and to breaking up the code, where you talk loosely coupled, one-way coupling, how exactly how you start to begin tackling that?
Right. So for the benefit of the people online, I probably didn't hear that. The question is, how do we incorporate the various physics models and the multiple scales that are at play, and how do we make that all work together? And so we do the solutions using an operator splitting method. So the hydrodynamics happens, and then you do the transport. Each of the transport operators happens separately, and you sort of update things like the electron and ion temperatures along the way. And so we do it's ion conduction, laser ray trace, electron coupling, or electron conduction, and then move into the radiation and transport and burn. And so each of those things happens separately, and the time step is checked at each of those. And so we maintain an explicit time step that is at least forward looking, is designed to be small enough that you will be capturing the relevant physics and the time scale.
Did you ever feel limited by your computational resources? You use some of the best computing resources in the country, but like, did you ever feel limited by that?
I feel like that's a loaded question. The question was, do I ever feel limited by my computational resources? Everybody always wants more. Whenever you give somebody something, they'll always happily trade it for a little more. But do I realize the privilege that I have for the enormous resources we're able to bring to bear on this problem? Absolutely. Our computer center is the best I've ever worked with. The people that support it are fantastic. The computers are so amazing. And so personally, it's a rare occasion that I'm like, oh man, I really need more power than I have. But for some of these big hero calculations, like these big 3D calculations, we'd love to be able to do those in production. But that's not realistic. So, do I feel limited? No, I feel very fortunate. But, if they would give me twice as much power, I wouldn't say no.
Awesome, thanks.
So the question was, how does this interact with the nuclear weapons mission at Lawrence Livermore? I would say that one of the primary missions of Lawrence Livermore is promoting national security. And part of their mission in that is their nuclear weapons duties. But we are also a big pillar of what we do is maintaining a strong scientific community and students and scientists trained in plasma physics and high energy science. And so that is the pillar that we work on. So we are learning things about plasma physics and benefiting the country in that way, and hopefully eventually letting this lead to fusion energy.
Of the upcoming steps that y'all are going to work for future experiments, which ones are you most looking forward to?
So for all the steps that we have going forward, which is the one I'm most looking forward to in terms of advancing fusion? It's hard to say. It's also exciting, but I think trying to more reliably and more frequently get high yield, try to get above the 3 megajoules that we got. I think if we could even get to 5 megajoules from a 2 megajoule laser, wow, wouldn't that be exciting? And I think there's a lot of really cool work going on the more modeling side of, well, okay, what if you had a 5 megajoule laser or a 10 megajoule laser? What could you do then? And sort of starting to ask those questions. And at the same time, trying to think about, well, if you're going to move on to fusion power plant, what are the practicalities that would have to change? And what are the things we have to learn? Our whole arms right now are made out of gold. Sort of the estimate we always throw out is, if you're going to make a power plant out of this, you got to fire one of these things off 10 times a second. That's a lot of gold, and gold is very expensive. So, what other high Z material could you use that is cheap? And could you still make work with 2 megajoules or 5 megajoules or whatever? So I think it's we've been so focused on this 2 megajoule laser with these gold holons or depleted uranium holons that now it's sort of, well, what if? So we get to kind of play a little bit more in that, while still, it's not really play because we're still very focused on the goal, but it opens up a bigger design space to get to think about.
You're under the portion of your code to run on graphics processing. How much of your code are you planning to do that with, and what kind of speed up is it to stay against your running?
I mean, I think the way things are moving, a lot of these supercomputers are moving most of their floating point operations onto the GPUs. So I suspect eventually much of what we do will wind up working there. I think CPUs will always have their role, and I think we'll probably always be using them. Right now, our strategy, because we're a very small team, and you saw the list of all of us, is to work on the things that are the most expensive. So we often use, in our Horon calculations, we use a Monte Carlo photon transport, implicit Monte Carlo photon transport. So that's a very expensive one. We have somebody who's working very hard on making that work efficiently on the graphics processors. But people in here that do Monte Carlo know that it's now poking at the memory very randomly, because I'm not systematically marching through a mesh and saying, okay, I'm going to operate on this zone and then this zone and this zone, and they're all sitting in one cache line. But I'm like, oh, I went into this zone, right? Access all this data. Oh, but then I transited over to this other zone here that in memory is, halfway across the DRAM chip. And so you've got a lot of cache hits on the memory, and that's an issue for performance on the CPUs and the GPUs. Oh, Lord help you. So, for very targeted problems, you see people quote like, oh, I came up with it. I ported my minimization calculation from my CPU to my GPU and I got 1,000 times faster. That's, I don't think, realistic for something like Monte Carlo photonics, where you're randomly poking the memory. But you have sort of two benchmarks. Maybe you can get it to be faster. I think right now, maybe a factor of a few, maybe a factor of many. But if 90% of your floating point operations are going to be on the GPU and only a few percent on your CPU, even if your performance isn't very good, you've got a lot of flops to play with. So even if you don't speed up, you might still win just by getting the graphics processor to be a part of the equation.
You mentioned in your talk having to worry about things like large angle Coulomb scattering.
Mm-hmm.
Whenever you compress something down to something that small and you get that high of a density of material, how much do you have to worry about even the neutrons in that? Is that something you have to account for in the model, or are they pretty much just there and gone?
We've looked into that. At NIF scale, they're there and gone. But you could imagine that if you go to high enough yield in a practical fusion plant, you might have to do it. We need to study it more, I guess. It's I think something of an open question, but it isn't a question. It's not a done deal. The question was, I'm sorry if I didn't repeat this for the Zoom folks, was do you need to account for neutron scattering down in the hotspot? Thanks. There was a question up there.
When we're planning to
so the question is, how often do you have to have a new Horon or fire at a new target for a power plant? And I mean, that I'm sure it's still a question, and detailed designs, the details of a design will tell you the real answer. 10 times a second is the number that I've heard thrown out for many years, since long before we got ignition. So that's sort of the ballpark estimate people toss around. So a lot higher frequency than we do now. Well, for a power plant, the question is, can the laser run continuously to do this, and how much time you need between shots? NIF, we do a handful of shots a day. But it was never designed to be a power plant sort of device. It's a flash lamp driven neodymium glass laser. It's just, it can't handle the kind of stress that 10 shots a second would throw at you. But laser technology has come a long way in 30 years. So I think there are realistic ideas for how you could build a rep rate laser that would be able to do this. And the experiments themselves, the laser pulses are only 10, 20 nanoseconds long. So
One question.
So, with regards to fundamental plasma physics, you showed this kind of a bar where racing through some really interesting, states of plasma. Strongly coupled, warm dense matters, and then passing through permeable matters to, really challenging physics. Do you see this now as a platform to help understand these states of matter? As far as I understand, these are still kind of fairly not well understood strongly coupled in many body interacting systems that are going to have different views. So do you see this as a platform to investigate these states of matter, or do we know it well enough now that it's inconsequential?
okay, so the question was, so we're going through all these very extreme plasma states and material states. And do we understand all of that well enough to say that's a done problem, or is this now a platform for doing studies of and trying to learn more about these kind of materials and plasma conditions, and including things like Fermi degeneracy? I would say there are a lot of open questions here, and I think NIF and the Omega laser at University of Rochester and many other places are good sources of experiments to study these. No, I think there's still a lot of uncertainties, and in our calculations, some things we understand very well, some things we'll have an equation of state that we use for some of these plasmas, and we think, okay, this is our best go at it. And we've had some molecular dynamics calculations say this is the best. And then we start taking data and realizing this isn't doing the best. So then we look at the data. There are people that do focused experiments on things like this, people that do more molecular dynamics calculations, and then they come back, okay, here's an updated, a better equation of state. But I think there's still a lot of uncertainties involved in all of this from beginning to end. And so there's a vast amounts of area for people to study and learn a lot more, because these are very difficult things to deal with, very difficult to diagnose, even in focused experiments, let alone, the kind of whole coupled NIF experiments that we do, trying to tease apart, what one little detail are we getting wrong. Well, we're probably getting many little details wrong.
Sorry, yeah. So just came up with questions. We can take probably 3 or 4 more, but we're running a bit over time. But anyways, I think they want to keep the discussion going. There was a question with different, yeah.
First of all, thank you for the really next one. So I know previously you kind of skip the details on the 3D modeling of the laser. I just wanted to know a little bit of the highlights of the minutes.
Okay, so the question was, what are the highlights in modeling the laser in 3D? So the model that we use is a standard ray trace, 3-dimensional ray trace. And the primary physics mechanism that we include, or physics mechanisms that we include for these types of experiments are inverse Bremsstrahlung is the process of deposition primarily. And then the primary, we've tuned away things like Raman's backscatter and Brillouin backscatter because they're energy loss mechanisms and potentially can damage the laser. So we've tried to be constrained to a phase space where those aren't an issue. And then I mentioned the crossbeam energy transfer, which is an ion acoustic wave mediated instability that transfers energy from one beam to another. And the way we do that in a nutshell is we trace the rays through the mesh and we accumulate the laser intensities and the intensity weighted average direction of all the rays in each zone. And then we say, okay, now let's trace the rays again through that, but now include the effect of that transfer. And we do that. There's a whole bunch of plasma theory that was on my slides, wherever it was. But we can calculate a coupling coefficient that will say, okay, given these intensity maps, we know how much energy should transfer between this beam and this beam. And we do that on a ray by ray basis and pairwise between all the beams. That updates the propagation of the laser power. And then we just have to keep iterating on that until it converges. Hopefully.
One more question over there.
Yeah, so you mentioned ion acoustic wave, but I was wondering what other missing physics that you were initially was that you had to add into the model, once you confirm the experiments? Does anything else stand out there?
Well, the question is, what physics did we add along the way that we didn't necessarily know we needed, or that we just didn't have? Along the way, we realized that Raman backscatter was a major issue, and so a model was developed and added. And around the time it was ready, we had tuned ourselves away from that regime, which was fine with everybody because it was nothing but an energy loss. But we did add that capability. I think there was suspicion that it would be an issue, but we didn't have a particularly good model for it at the beginning. The crossbeam energy transfer was being developed sort of around the same time, as an idea was being developed around the same time NIF started experiments. So some of the early experiments were just demonstrating it. And so that model was sort of developed on the fly as experiments were going on, and we started playing with it. So again, we sort of knew that was coming, but that one happened along the way. The Monte Carlo neutronics was also added. That was something that we knew we wanted to have, but was added, or that was just in time. That was done sort of as experiments began. I think probably the biggest area where we've had improvements is in an equation of state and opacity modeling. And neither of those are really my area. I'm not an atomic physics guy, so I don't want to pretend to speak to the details of what happened there, because I'll just talk myself in a circle. But I think probably the biggest changes in physics modeling has been in those two areas.
Two more questions to go. Also remote, raise your hand, please, if you have questions.
How close is your models not to like measure value? Is it like 1-2%, or is it more like 10 to 20 like that?
So the question is, how good do our models match the data that we're actually getting? I don't want to answer that. I would say overall, I think the feeling is we do a good job. There are certainly uncertainties, though, still in equation of state, opacity, and other things. So there are places where we know we have fudge factors that get included. And we don't always have a good physics basis for it. But we are able to generally say for example, one of the things people do is they will monkey with the opacity and emissivity of gold. And we don't have a good, we don't have a theory that says, oh, you should add this multiplier to that opacity and emissivity at these temperatures. But we are able to say, okay, we did a series of experiments, we did a couple of experiments, we tweak what those multipliers are, and then we keep doing experiments where we're changing the targets in the laser pulse kind of around the neighborhood of parameter space for that. And the model will be predictive using those multipliers. It's hard for me to say matching to some percent, because it really depends on what measurable you're trying to compare to, and then, well, what's the error bar on the measurable? Because we're really comparing to the data where we don't really understand the instrument response function perfectly. So there's a lot of wiggle room on both sides, but enough that we were able to kind of systematically walk our way through that chart from the low foot to the high foot to the HDC to the hybrid, improving the hybrid, and then to ignition. So we're doing that well. But can we, from first principles, calculate everything perfectly without any uncertainty? No, not even close.
One more final question.
Do you look into other fuels that lot of this was specifically?
The question is, do we look at other fuels? I focused in my talk on DT. DT has the highest reaction rate. So it's the easiest and lowest temperature plasma to be able to do this with. You could in principle do it. Well, you could do it, any of the stellar cycles you could use. Probably the most obvious next contender would be to get rid of the tritium and just use deuterium-deuterium reactions. But that definitely requires higher densities and or temperatures. So the DT was the easiest, fastest route to get there. Just because of the largest the amount of energy you liberate, and the reaction rate, say, is a function of ion temperature.
Well, I think we thank Scott again for coming out and doing this. And feel free to come up if you have any particular discussions. I think you can hang out here for a couple more minutes if you want.
Sorry.
Congrats.
Thank you.
Thank you so much.
Wow.
It's awesome.
Thank you.
Thank you. Yeah, how does